Okay. So, good afternoon, everyone. Thank you for letting me be here. I'm here on behalf of my colleague Niels, who sadly can't attend today. And I'm going to talk about security, especially the tool Scapy and its advances to test modern automotive Ethernet protocols. First off, sorry to everyone who can speak French. Many have tried to tell me I need to tell Scapy with a French accent. They all failed. Just imagine I say it with a French accent, okay? So, today I'm first want to introduce Scapy, how it works, what the goal of Scapy is, then a short history of Scapy. Today we heard a lot of new ideas, new tools. Scapy is quite the opposite. The first presentation on Scapy was at 2003. So quite a long-living tool. Then I'm going to talk about how it went from Ethernet-based testing to more automotive, and then to the new present evolving protocols like SecOC, SOME IP, everything that came with Automotive Ethernet. So, Scapy. Scapy is a packet manipulation tool which allows us to create protocol packages, work with them, send them, receive them, and to test a target. So here we see how a package is crafted. Scapy uses the ISO-OSI layer principle. So we just take the different layers and stack them on top of another. Scapy is a Python library, so it's all Python code. And here we see an example of an ICMP ping. So we have an Ethernet frame, when we have an IP frame, and when we have an ICMP frame. And this is, actually it in the basics. This will create a fully valid package that we can send then over Ethernet to try and ping it up the POM. The idea behind the building of a package is that we can give every field a value. So here you see, afterwards I showed the package, we see every value is actually has a predefined value, but we don't need to. So we can specifically craft the package in a way so we test what we want to test. The rest will all be run to valid defaults. Valid default means for Ethernet, it will take the operating system MAC address or the operating system IP address. The length fields will be automatically calculated if we don't give it a value. Nevertheless, if we want to do anything to the package, we can do it to the package. So if there's a length value, it doesn't need to be the length of the data. We can give it any value we want, and it will be the value that's actually sent over the cable. And then after we created our package, another nice function about Scapy is we can use the built-in sending functions, so we don't need to care about sockets at all. And it also has a send and receive mechanic. The send and receive automatically tries to match the answer to the package we send. So if we send the ICMP package and on the cable there's a HTTP package coming back, it will not be recognized as answer to the ICMP. Instead, it will wait till it gets an ICMP answer, or it will just say, hey, we got no answer. And with that mechanism, we can use it for to create any package we want, send it, and then see if there's an answer to it. That's the basics of Scapy in 2003. If we look a little bit into the future, so now in the past, but in the future of 2003, 2018, this is how the implemented stack of Scapy looks like. So as you can see, we have a classic Ethernet stack, IPv4, IPv6, TCP/UDP, TLS, everything you would need to test Ethernet. But there are no automotive specific protocols in here. There's no, CAN, for example, had no support at all. It was just Ethernet testing tool, not just Ethernet. There are other protocols like Wi-Fi, but I will ignore them for this talk. Then, after 2018, there was a research project started at the OTH Regensburg, which then tried to forward test automatization in cars, which then added the automotive side to Scapy mainly. And here we see what happened in the next few years. We got full CAN support, SOTP support, and automotive specific application protocols like UDS, GM, LAN, was the first draft of some IP, even some debugging interfaces like TCP added to Scapy. And then currently we can just craft packages, send them, and look for an answer. The whole thing, of course, has over the years gotten more and more functions. And one function I want to present are the scanners, especially UDS scanning. There are scanners for multiple protocols that try to enumerate basically everything what's possible in the standard. So one fair warning in front, if before you use the scanners, the scanner have options to be configured, of course, but per default, they try to scan the complete valid range, which means here in the example, we have UDS. UDS, read data by identifier, are 2 bytes, so 65,000 messages to be scanned. So the scanner can take a while. Here you see the code that's necessary to do a simple UDS scan. The first few lines are just imports, and we have 4 lines. First, example is on CAN, ISOTP, so we need to create a socket which contains the IDs. So the operating system does know which is the answer port, which is the receiving port of the ECU. And then we use the UDS scanner function. And here, the main thing is we have so-called test cases, and these test cases are called enumerators. And here, for example, for UDS, we have an enumerator for every standardized service that's in the standard. So every service can be scanned. So if we do a basic scan just for UDS services, we get a picture like this. We will get, we tested every service of the ECU and then get answers of that service of the ECU. Request out of range is per default filtered. You can show it, but in most cases, it doesn't make sense to see 250 request out of ranges. Here, one thing you may notice, you will see no positive response. Per default, the scanners are trying to be non-intrusive. What does it mean? Scapy can actually be used on cars, and if we want to scan a car, we don't want to accidentally trigger any functions we don't want to. For example, if we do a routine scan, we don't want to trigger all routines there are, because that will most likely lead to some errors, and when you need to go to a repair shop to get them fixed. Therefore, Scapy, for the service scan example, where it sends basically, I want to execute service diagnostic session control, but then it doesn't tell the ECU in which session it does want to change. So in that case, if diagnostic session control is supported, we will get a negative response, which is not request out of range. So one thing about ECUs, we can now see the supported services, but we can only see it in a default session. Normally, ECU, UDS, like by diagnostic stack, works like a state machine. So we have many different states. On most ECUs, we even have 2 UDS implementations, one for the application, one for the bootloader. And therefore, normally, if we want to check everything of the ECU, we would need to go into every state of the ECU. This is where the UDS scanner gets its logic from. So behind the scenes, there are some services defined that are most commonly used in the industry that change the state of the ECU. Diagnostic session control. Okay, I want to change session is obviously a code for I want to change state. We can go into the extended diagnostic session or into the bootloader. When we have ECU reset, it will reset the whole thing back to the normal. When we have communication control, which some like that is proprietary, some OEMs require it, and then we'll give different answers. And when we have, of course, routine control, and this list is not complete, we have, for example, also security access and the new authenticate service. And the idea behind the scanner is that before we do the scan, for example, for every service that's available, we first try to build a state picture of the ECU. The scan takes a minute. So here you see an example tree, 5 points if you can guess which OEM this is, of the ECU. And here we see the different sessions. We always start in the default session, when we have an extended diagnostic session, and when we have a programming session. That's the normal standardized thing. And then we have also different security access levels. And to find out what the ECU really supports, we need to make a service scan. For example, let's see, does the ECU support read memory by address? Then we need to ask the ECU, hey, I want to execute read memory by address for every state there is. So we can really check if we get a positive response in one case. And the scanner does this, it generates the picture and does this picture automatically. If you add any service enumerated to the scan, which can change the state, for example, diagnostic session control. In the next picture here, I have example, this is what the scan output looks like if you just do diagnostic session control, if you just add diagnostic session control to the scan. And here you will see, we will get different answers in different states. The most prominent thing is always the bootloader. So session 2 will have drastically different answers than any other sessions. Also, the interesting thing from a security perspective are not session 1 and session 3, it's session 2 and the proprietary sessions we see that are used non-standardized, and where we can then start looking for it. One thing if you use such a scanner is, what we look for is for the prominent security that's denied. Here in that service scan, it's rather uninteresting, but then, for example, we check the read data by identifiers or the available routines on the ECU. And it happens a lot that the routines in a ECU are secured in session 1, session 3. But then if you change the state machine to bootloader and try the same routine, it suddenly isn't secured anymore by security access because they just forgot or didn't test. So yeah, it's really important that all these answers are consistent with the spec normally. Or if you get a security access denied in one session, you should get security access denied in every session normally. Yeah, this picture is quite a lot for that picture. Here, just a warning, if you do like routine control scans, read data by identifier scans, it's always 65,000 requests times the available sessions or states of the ECU. So the normal behavior is you would, on Friday, you would plug everything in, start the scanner, and then come back on Monday when you have the results. Even with Automotive Ethernet, it takes quite a while to scan everything. This was, for example, for the UDS scanner. There are more scanners available also for automotive protocol. For example, ISOTP scanner, XTP scanner, GMLAN scanner, if someone still uses GMLAN, OPD scanner, and so on. And this is how the picture looked like, yes, 1.5 years ago. We see basic automotive protocols are now implemented. We have CAN, we have CAN-FT, we have the transportation protocols, and we have a few applications. Now to the recent changes. So one advantage using Scapy, which we didn't know that much in 2018, is that the automotive industry is changing back to Ethernet a lot. So having all the implementation of IPv4, IPv6, TCP, UDP, we don't need to do it anymore. But we need to consider the new automotive protocols that are being used. For example, DoIP, diagnostic over IP. We are now speaking UDS over Ethernet with our own transport protocol. We have SOME IP, we have SecOC, we have AUTOSAR PDUs, and so on. And yeah, now I want to dive a bit deeper into these additions. First off, Ethernet versus automotive Ethernet. For tester view, there's actually no difference between Ethernet or automotive Ethernet. Ethernet is a different cable. Ethernet has 8 cables. If you plug OBD2 in, Ethernet has 4 cables. Automotive Ethernet has 2 cables. Yeah, the physical layer is different. But in total, if I plug Ethernet into a PC, doesn't matter which one, Windows, Linux, Mac, it will always come out as Ethernet. If for automotive Ethernet, I need an adapter or a media converter, which converts it to USB or to Ethernet, so I can plug it into the laptop, because the laptop don't usually have automotive Ethernet plugs. But then it will also come up for the operating system as Ethernet. So all tools that I can use for Ethernet, I can also use for automotive Ethernet. Well, ISO-OSI layers are exactly the same. We also use Ether frames, IP frames, and so on. So there's no difference at all. One thing here, we are currently doing a crowd supply for open source USB to Ethernet T1 adapter, which can be controlled over software. There's one thing about automotive Ethernet. If you plug Ethernet in, it will automatically come up. For automotive Ethernet, it's a master-slave protocol, and it has a certain speed, and we need to get all the settings right, otherwise you will get no connection. And yeah, we try to make hardware which is software controllable, so we can change master-slave and the speed. Yeah, let's look at the first thing today, which is new, diagnostic over IP versus CAN. So on CAN, sending UDS is actually quite simple. We can just get 8-byte message out, and we just need a ISOTP header, which is 1 byte. And so we can just send 8 bytes over CAN. It is ready to use UDS message. It will be interpreted by the ECU, and when we get our answer. For Ethernet, Ethernet is cool and all and has a lot of advantages, but big disadvantage is it gets a lot more complicated if you look at the use protocols. Just to send UDS, we now need Ethernet frame, VLAN frame, IPv4 or IPv6, depending on what is used, TCP and UDP, because DoIP uses both TCP and UDP. And then we can send the UDS frame. And all the errors that go down indicate this is not a single message, it's actually a handshake that's needed. So we can't even send one UDS message. First, we need to make a few handshakes so the ECU even knows we are talking with him. The first handshake is up or any or by used protocol that's used to identify which IPv4 address the ECU has, or we have. When we need to make a TCP handshake, which is also a back and forth, and when we need to, in DoIP, do a routing activation. Which means previously on CAN 8-byte, on CANFD, we used padding 64-byte were sufficient to send UDS. Now we have, just for the simple DoIP request, we have multiple 100 bytes. Just from a testing perspective, which it also means that there's a lot more code in the ECU that needs to be gone through so the UDS matches can be interpreted. So first we need to have IPv4, IPv6 logic, when we have the TCP UGP logic, when we have the DoIP logic, I have VLAN and Ethernet logic. And so every one of these stacks can have errors. There are Ethernet, VLANs, IPv4, IPv6, TCP, and UDP are long available. There are a lot of known attacks against them. So we can test a lot in these additional used protocols. Now, this is actually the old standard. Now to the new standard, it gets easier. We need to first make a DoIP connection on port 13,400 when we close the port again and when we open a TLS connection to speak UDS. And yeah, you see the picture gets longer and longer. Now we have 5 handshakes just for that. And we have also the TLS handshake, which is also quite complicated and a lot prone to errors, let's say. At that point, we went from using 8 bytes to send a UDS message to more than 1,000, just to get the first UDS message to the ECU. In Scapy, we can, of course, build our own packages, like we saw with Ethernet, VLAN, IPv4, TCP, TLS, DoIP, and so on. But my problem is if we test a specific protocol, we want to do this. But if we test higher protocols, for example, if we just want to test DoIP or UDS, we don't want to build the whole package all the time, because we want just, hey, please use the valid values. We are fine if you do it for us. And for that, we changed the DoIP socket so it fully automates the DoIP TLS handshake. So here you see the top function, the DoIP socket. You just give it an IP, it tries to connect with it, and then it will automate the ARP, it will automate the TCP handshake. If you use the DoIP socket, you need to do the routing activation was safe. There's also a UDS socket, which even does the routing activation. And down here, you see now the advanced DoIP socket usage. You can give it a certificate and say, use that certificate, and then it will automatically force this behavior. So it will try to reach port 13,400, then close the connection, and then tries to do a TLS handshake with the ECU without us needing to build any packages. The additional code here is just loading in the certificate. Depending on the ECU, this is not needed. And then we can start sending DoIP to the ECU. So DoIP over TLS, new feature, was a lot simplified. We can just use the DoIP socket and tell him to force TLS, so we will do everything automatically for us. Then one advanced feature, which now got a lot more attention, is how do we simulate ECUs? ECU simulation can be done in Scapy with automatons, so they work just like a state automaton. We have an initial state. Then we have a condition, which is the transition to another state. And then we have a final state, and an action is called if a transition was successful. We can use this to I will skip one slide here, to make an automaton which automatically answers any response. So we can emulate a ECU. We do this by using a function called receive condition. If we get, so our automaton is always initialized with a socket. And once we gave it a socket, it gets all the packages of the socket. And if it receives a message, it will then call this function here. It tries to decode it and then give a valid UDS response. So this is just a really simple UDS implementation. We can just change to session 1. That's it. And with that automaton, we can effectively simulate ECUs. So I'm a penetration tester. I want to crash stuff. I mean, simulating is cool for unit tests. What can we do? Turns out we need ECU simulation a lot more if we use Automotive Ethernet. The main reason is many protocols don't use the I send a message on CAN and wait for an answer anymore. Instead, we are doing handshakes. We are communicating actively back and forth with the ECU to do over-the-air update, SOME IP, AUTOSAR PDUs, and so on. Therefore, we can take this ECU simulation feature of Scapy to make malicious servers that communicate with the ECU and try to attack him. Here I have an example. We can make a very quick HTTP server which will answer to if the ECU tries to head or get a file. So some OEMs use HTTP servers for their OTAs. In that case, we can just emulate such a ECU and try if the ECU fetches our wrong over-the-air update flash file. One additional thing, we can also test SOME IP over it. So SOME IP is normally used as, we have a discovery phase when we say, hey, we offer that, or the ECU tells us what he tries to find. When we offer it him, when he tries to subscribe, when we need to acknowledge it. So it's a lot of back and forth before we can send the AUTOSAR PDUs. And with the automatons, we can make a SOME IP server, which can then have dedicated errors built in. So what happens if we send the wrong PDU ID? What happens if we try to do SOME IP on the wrong ports? What happens if we suddenly change IP address and so on? With that, simulation, we can afterwards, we also, after we did SOME IP correctly, then try to fuzz AUTOSAR PDUs. AUTOSAR PDUs, normally called AUTOSAR PDUs, now come also with SecOC. SecOC is actually a big challenge for open source because in the normal world, ideal world, SecOC is standardized. We have clear definitions. Everyone uses we have just 3 crypto profiles. We have a well-defined freshness value. We have well-defined functions we use and how we use it. We have reset counter, we have trip counter, and so on. So everything looks quite nice. We can implement that. And when we have a problem of reality, every OEM uses basically his own nonsense of how he does SecOC. There's unclarity in how do we even generate the MAC, what do we hash? If I send a CAN message, do I hash the ID with it? Do I hash the ID with it? Do I just take the data? Every OEM does it differently. Do I use padding? Don't I use padding? We have a lot of custom written key exchange. Therefore, it's hard to implement. We tried to solve that issue in Scapy by making classes that can be inherited from, which basically they implement that ideal world. And if you then are hit by reality, you need to look at the specs, how it really works. There's a bug there, please ignore it. It needs to be called which run. And it's basically still in discussion how we should handle this SOC problem. One problem is also we tried to add a few OEM-specific information in Scapy. When there were a few letters which told us we should stop doing it, and we can't implement SecOC for every OEM because we are also restricted by NDAs. So this is SecOC as far as we can bring it. We can implement the ideal world, and if you then are hit by reality, you need to inherit the ideal world and then change it to whatever the OEM is doing. Yeah. One last thing, which is new, is also full support of UTS authentication service. So service 29. This is how modern diagnostic access looks like. We get a certificate from OEM backend, send the certificate to the ECU. When the ECU gives a challenge, when we solve a challenge by the OEM backend, and when we send it back. Previously, seed key algorithms were used. So we ask the ECU, hey, I want to authenticate, give us a seed. We got a random number, then we need to do magic with the random number and send it back. It was way easier for the ECU to check this kind of authentication because it just needs to calculate one value from a random number and see if the two values matches. Now we have a problem that we have complicated certificate passes inside the ECU. And the problem with the certificate passes is they are way more complicated than seed key algorithms. So they need to pass correctly. So we have buffer overflows, memory leaks, integer overflows in a pass. Then they just say it because normally it should be done. It should be obvious. You need to first check the signature before you do anything else with a certificate. So don't set the date to the start date of a certificate if the signature is wrong. And yeah, also, yeah, all the error handling that comes with certificate passing. So Scapy is not made for certificate fuzzing, but Scapy can send the certificate pretty easily by just making the package. One thing we do here is we use other open source projects like Frankenzert, which are dedicated certificate fuzzers, or they can produce 10,000 of certificates, every certificate with its own error. And then, yeah, you send 10,000 certificates to the ECU and look how it reacts and if the parser is implemented to the edge cases correctly. Yeah, that was the new stuff of Scapy. Thank you for your patience. If you are also interested, please into the Ethernet hardware interface, please feel free to follow us at Cloud Supply. Thank you.
So any question? But I do have a question. So thanks for the introduction to the Scapy project. So is this an open source project?
Yes.
How can people contribute if they want to?
Yeah, so it's fully open source since 2003, and yeah, everyone can contribute. Just there are a lot of open tickets, a lot of to-dos. Yeah, just write with the maintainers, or we get a lot of pull requests by people who did stuff with Scapy and just wanted added to mainline.
So maybe you could consider donating it to the foundation if it is open source, but
yeah, I think we'll have. So it's under GNU Public License 2.0.
Okay. So I do have a general question to the audience. So this is the first time we really are bringing security topics to our community day and to our working group. So how many of you are familiar with this concept? Yes. Okay.
Yes.
So A few, very few. Okay. So do you find this of interest to the community? Do you think we should move more in this direction? So who says yes, please raise your hand. Okay, good to know. That's been very interesting and helpful then. Thank you very much. I'm checking if there's one question.
Oh.
Can some IP protocol be implemented on like
some IP on CAN is like the whole idea of some IP is that you can subscribe to PDUs which have IDs, and on CAN every message has an ID. So on CAN you don't need that mechanism to subscribe because you get the later. Yes.
it makes no sense. Yeah, I would. Okay, so that's been answered. Then thanks to speaker again. Thank you, Jonas. I don't.